Hello and welcome everybody and the series of AP Chemistry for Unit 5. Today we'll cover the topics of introductions to the rate law. So we'll introduce you how to write the rate law, expressions in addition to components of the rate law in terms of the order of reactions, the overall order of reactions in addition to the proportionality constant, which is called the rate constant. So let's start. As we can see, we have reaction between reactant A and B to produce C and D. If you want to write the rate law expression, you have to put the three components. The first component is the K value, which is the rate constant or the proportionality constant. What you should know about proportionality constant, it's a temperature dependent. So in other words, if you increase the temperature, the value of K will increase. So we can say that the rate of reaction is affected by temperature in terms of the value of K. The second part of the rate law expression is the concentration of reactants. So we can say that we have reactant A and B. So their concentrations are represented in terms of square brackets. So these are the concentration of reactant A and B. The last part of the rate law expression is the exponents or the powers. The powers are called reaction order. So I can say that N represents the order with respect to B, and M represents the order with respect to A. If you add the two powers, like the two orders together, you will end up with something called the overall reaction order, which is the summation of the whole orders. All right, let's talk about the rate constant in more details. The rate constant K can tell me a lot of informations about the order of the reaction. For example, if you look at the order of zero reactions, the unit of the value of K is, as we can see, it's represented by m per second. And keep in mind the m per second, which is the unit molar per second, which is the unit of concentrations, that represents mole per liter. So the mole per liter is represented by molarity, which is m. And the same thing for a first order, as we can see, the unit of K is s to the power -1. For unit 2, as we can see, as follow here. You have to put in your mind, since the time is represented by s, which means it's a second, sometimes we can deal with a day, sometimes we can deal with a unit of time in terms of, for example, like day to the power -1. It could be an hour to the -1. So it's okay to have a time raised to the power -1, as we can see in here. If you want to determine how to write or how to determine the rate constant unit, let's take an example. Let's say when it's a second order. I just want to write something like, if we want to have a rate of a second order, we can say this is the value of K, and we have, let's say, A squared. Okay, the unit of the rate of reactions is molar per second, and we have K value in here. The unit of the concentration, you just notice that it's molar squared, right? Perfect. Now, since we have molar per second in here, and we have the value of K, and here we have molar times molar, at that point we can cancel the molarity in both sides via reaction. And if you want to make it like some of, by just doing some math in here, the S -1 equals K M. 1 over S is equal to K M. Okay, then the value of K is equal to 1 over S dot M, which is the same thing as M to the power -1, S to the power -1. And it's the same thing as in here. So the value of the unit, or the unit of the rate constant, can tell me about the overall order of reaction. And now, if we want to write the rate law has an expressions, as we can see, for the following reaction, which is A plus 2B equals 2C. So my target as a scientist is determining the values of the orders of reactants in addition to the value of K. So writing the rate law in this form is not enough. You're supposed to find the value of y, x in addition to the value of k with respect to its unit. How can I do this process? One of the methods that are used for determining the rate law is called the initial rate method, in which we are measuring the initial rates of the reactants. But how can we do this process? The process is done actually by differentiating the concentration of reactants and make them sometimes constant. I mean, in other words, for example, if we look at experiment number 1 and number 2, we can notice that the concentration of A is fixed, whereas the concentration of B is changed. So at that point, we will see what will happen as a result of it changing the concentration of B on the rate of reaction. So at that point, for example, if we take experiment 1 and 2, since A is fixed, but if we change the concentration of B, I mean like it's doubled. It was 0.05 and now it becomes 0.1. So we can see that the rate of reaction is also doubled. Since we have double, like it's doubled and it's doubled in here, then the order of B for sure is a first order. Okay, from this one, I can say that the order for B is first order. Now we're going to determine the order of A. At that point, we have to take different concentration of A and constant concentration of B. So we can see this process in equation or experiment 2 and experiment 4. So let's take the concentration, which was 0.05, and now it becomes 0.20, which means it's a quadruple. And since the concentration of B remains constant in both the experiment, now what happened to the rate of reaction? The rate of reactions was 6 times 10 to the power negative 3, and now it becomes 2.4 times 10 to the power negative 2, which means the rate is also quadruple. So since this is a quadruple, I mean it's increased by factor 4, and this is the same thing, increased by factor 4. Both are increased in the same way. It's first order with respect to A. So since it's first order with respect to A, and it's the same thing with B, so I can say the rate of reaction is equal to K, A, and B. And we can notice that the overall order of this reaction is 2 because this is 1 and this is 1. The summation of the two orders is equal to 2. Let's just see here, calculate the value of rate constant. Okay, how can I determine the rate constant? Let's go back again here. You can choose any value since the rate constant is at temperature dependent and this experiment is done at the same temperature. So the value of K for experiment 1, 2, 3, and 4 is constant. It's the same. So I have to say, let's use randomly like experiment number 1. If we have 3 times 10 to the power negative 3, here we have K, which is unknown to me. The concentration of A is 0.05, and this is for B, it's 0.052. Okay, so here we have the K value is multiplied by 0.0025, and here we have 3 times 10 to the power negative 3. Okay, by dividing over this number. Okay, then the value of K is equal to 1.2. Since the reaction is a second order, how can I determine the unit of K? So I just want to work out this in here. Actually, you can memorize the values of the units, but for me, I don't like memorizing. So we can say if the rate for a second order is like molar per second and it's equal to K, and here we have molar and we have another molar in here. We can cancel out the molars on both sides. So it's 1 over S, and here we have the K, and this is in here. If you do some math, then the value of K is equal to 1 over s, which is -1 as -1. If you want to write it like in terms of mole per liter, since the molarity here is 1 over mole per liter, it's going to be liter mole to the power -1 and s to the power -1. So this is true and this is true. So the value of K is 1.2 molar to the power -1 s to the power -1. C says, if another experiment is attempted with A and B, this is the initial concentration. What would be the initial rate of disappearance? This is a normal thing. We are going to substitute the value of concentration directly since the value of K is determined. So I can say this is 1.2, which is the value of K. The concentration of both A and B is 0.02, 0.02, 0.00048 molar per second. Okay, let's test your knowledge with another example. If you look at this one here, I'm going to write the rate law and the rate constant with its unit. In order to calculate the unit of A, we need different concentrations for A and identical concentration for B. So we notice that 2 and 3 are the best solution for that. Okay. So basically, we just like the concentration is a quadruple for A, and this remains constant. We can see that the rate of reaction remains constant. So there is no effect on changing the concentration of A on the rate of reaction. And at that point, we can say that the rate of reaction is independent of the concentration of A. And that's why the order is 0, because there's no change. It's not doubled here. It's not quadruple here. It's not a tripled nor doubled anything. So far the rate, the order of A is 0. Let's determine the order of B. So in order to calculate the order of B, we have to take different concentrations and identical concentrations of A. So it's done in experiment 1 and 2. These are fixed so far. We can notice that the concentration of B is tripled, and the rate is increased by factor 9. So since this is a tripled and it's increased by factor 9, then for sure the power of B is 2. Okay, so this is the idea. It's increased by factor 3, and here it's increased by factor 9. So this is for sure a double, or it's a second order with respect to B. Okay, so if you want to write the rate law, you can either write it in this form. You can say K, and this is A to the power 0 and B to the power 2, or you can say it's K to the multiplied by B to the power 2. Okay, since it's a second order, it's the same as the previous example. The order is the unit of K is equal to -1 as -1, or you can use it in terms of liter per mole to the power s. So these work. If you want to determine the value of K, we can substitute the value of B in here. Let's take any example, any random experiment. Let's take the first one, 1.1 times 10 to the power -6. The value of K is unknown, and this is the initial concentration, which is 0.2 squared. So the answer is equal to 2.75 times 10 to the power -5